Welcome to the 19th lecture of combinatorics. In the last class we were considering this problem, namely we have universe U and A1, A2, AK etc. So, this up to AK, k subsets of the universe U are given. So, we are considering finite U, and so what we are interested in is the number of elements in U minus A1 union A2 union A3 union up to AK, or in other words in the complement of A1 union A2 union up to AK, how many elements are there, in the complement of A1 union A2 union up to AK. In again we can easily see that this is equal to, by De Morgan's rules, we can easily see that that is equivalent to asking the cardinality of the complement of A1 intersection, the complement of A2 intersection, the complement of AK, right. How many members are there? We have discussed it all carefully in the last class, considering 2 set case and 3 set case, when k equal to 2, k3 equal to 3. Now, we are saying that the general formula for this thing can be given like this. It is equal to U minus, here U minus sum of the cardinalities of the AIs, you sum up the cardinalities of each set given, and plus the sum of the cardinalities of AI intersection AJ, where AI AJ, I not equal to J, any each 2 element subset of 1 to k you take, and those corresponding 2 subsets if you take and find the intersection, and those cardinalities you add together. There are k choose 2 such things, you have to add them together, and minus all possible 3 subsets of 1 to k you take, and the corresponding AI intersection AJ intersection AK you consider, right, and then re-add. So, this plus or minus you do until the last term will be minus or plus, depending on whether k is a odd number or even number, as you can easily see, right, because it is alternating plus and minus. So, that is the formula. How did we get the formula? The formula we guessed, in fact, we looked at the pattern of the formula when k equal to 2, that means when only 2 sets are there in the collection, that means A1 and A2 alone. Then we saw that there is U minus A minus B, that is minus of sum of A plus B, cardinalities of A and B. So, okay, A1, we can say A1 and A2, and plus A1 intersection A2, that was only 1 2 members means 2, and then the 3 members also, in the 3 members case also we considered the formula that had one more term, namely the last term being the intersection of all the 3 sets, that also followed the pattern. And actually we gave 2 kinds of arguments to show that this formula is correct. One was done as we wrote down the formula, means we kept on arguing and wrote down the formula, and then therefore it was correct. In the 2 cases, using the Venn diagram we were arguing. Now, it was like we want to find the members in U which are not in any of the AIs. So, you first take all the members in U, U, so that is cardinality of U, right, and then that is why we wrote U. Then we minus of the members in A1, minus of the members in A2. So, like this, A1 minus of the members in A2, minus of the members in A3, and so on, right. So, up to AK we can minus off. So, this would indeed give the answer if each this A1, A2, A3, AK were pairwise disjoint. So, AI intersection AJ was an empty set for every pair of I and j in 1 to k, this would have simply given, because we are subtracting things which we do not want, and then nothing is subtracted more than required. But unfortunately that is not the case. We will, because there will be several things, this A intersection A j will not be empty, many cases there will be non-empty intersections, and those members in A I intersection A j when it is not empty will get subtracted twice, that once for this, one for this, right. So that is why we told, okay, for instance, if there is a member in A I intersection A j, they got subtracted twice, therefore I have to re-add it, they got subtracted twice, so we have to re-add it. So we just re-added it, we decided to re-add this thing, and we did it for every pair I j. That was the next type of things, every pair I j, right, selected. But then we noticed that, okay, if a member was in more than 2 sets, that means let's say 3 sets, then initially they got subtracted 3 times. Once in, say, if a member was in A I intersection A j intersection A k, that member was subtracted for this one A I when it was as part of A I, that member contributed to the minus term in A j for A j, contributed to the minus term for A k also. That means minus 3 was subtracted, but then we re-added also, but then again 3 times it was re-added. So 3 times subtracted and 3 times re-added. So we would think that, okay, it was not subtracted at all, but it has to be subtracted. So we subtract such terms again, all A I A j A k intersection things. So we found out all triples, we found out, and then there are k choose 3 triples, okay, for k choose 3 triples of 1 to k. So this is k choose 3 for every triple in this set, k choose 3. So we find out the corresponding A I intersection A j intersection A k, and then that cardinality is subtracted off, right. Then we see that suppose there is a x which is in 4 elements, say A1, A2, A3 and A4, in the intersection of 4 elements, they got subtracted too many times. So we have to re-add it. This was the thing. We can carefully argue it and probably make it so that convince yourself that this will be the pattern or the formula. But again, we need a rigorous proof, though the proof is kind of in this direction only. So we need a neat proof for this thing. That's why we were following a counting argument, namely how much each member of the universe is contributing to the sum on the RHS, because we want those members in U which are not in any of the AIs to contribute exactly once, while those members in U, the universe, which are in at least one AI should contribute only 0. Then only we will get the correct count we are looking for, namely the cardinality of this intersection. That means the cardinality of the complement of this, right, then only we will get it. So now we will carefully look at this counting argument and prove that the formula we wrote down in the slide here is correct, right. So how do we do this thing? So we will consider just 2 cases. First case is when x element of U bar, so as we want it, A1 union A2 union AK. That means x, when x is in the complement of x is in the required set, that means yeah, this set. How does it contribute to the total sum? So we can go back to the slide. Here in the first term in U it is contributing 1, in the second term onwards it is not contributing at all. So, we can write it down here. So, in U it will contribute, but then remaining terms in none of the AIs it will contribute, because in AIs it is not there. Sigma AI cardinalities it will not contribute, because here it will contribute 1, here each of them it will contribute 0 only. Similarly, this kind of terms where I and j are considered and then AI intersection AJ is considered, right. Here it will only contribute 0 because it is not in AI or AJ, right. Similarly, IJK in 3 of them. So, for instance, none of AI AJK contains that member. So, this will be also it will be contributing to this sum also 0. I mean, any of the later coming terms it will be contributing 0 only. So, these terms won't be it won't be contributing to these terms. So, it will only contributing to the first term, namely 1, and its contribution is just 1 as we discussed, right. So, that is fine. Now, the second case is, suppose X is not in the required set. That means it is not in AI complement union, right. So, that means X is in some AIs. So, we will say that X belongs to exactly which AIs it belongs to. Let us say it belongs to AI 1, it belongs to AI 2 and it belongs to AI 3, say it belongs to AI T. Not that T is anything between 1 and K, because there are total K sets. We know that it belongs to at least 1, right. So, T, we will take the general case of it, it belongs to T. So, this is, and it does not belong to any of the other things. Actually, we can write it does not belongs to any of the other things. X does not belong to a IJ where J is not in, say, 1 to T, right. So, no other, only in this sets it belongs to, right, exactly T sets it belongs to, and these are the T sets in which X is present. Remaining sets does not contain X. In that case, what will happen to that X? Clearly, X will contribute 1 to this term, X will contribute 1 to this term, right, because it is there in U, and minus sigma AIs, all the AIs does not have X, right. So, but in exactly T AIs it is there, right. So, those T AIs it will contribute, say it is T choose 1, because out of those T things, if you take any one set, it is in this sum it is contributing, right. And the next term of this sort, right, IJ, any pair of sets, if you take AI intersection AJ kind of sets, for any pair IJ from 1 to K, that will X will contribute how many times? You know, if this I and J are A and AJ are such that X does not belongs to either AI or AJ, definitely it is not contributing to this AI intersection AJ, because it will not be there in it. So, only the pair of sets from the collection of sets, say AI 1, AI 2, AIT, in which X belongs to, right, any pair if you take from this thing, then that will contribute. How many pairs are there? Definitely T sets are there. Any T choose 2 sets which we can take from here. If you take the intersection of those such pairs, we will have X in it. So, it will be contributing. So, the total contribution here is T choose 2, right. T choose 2 will be the total contribution. So, the first it will contribute 1 to this thing. One is you can take it as T choose 0, right. Then the next term it will contribute a minus T choose 1, and then next term it will contribute a T choose 2, and the third term it will contribute a T choose 3, minus T choose 3. Why? Because that is sets of this form ijk aijk so for instance, so yeah, so three members of the collection is taken and their intersection cardinality is put here, but then x will belong to only those intersections of three tuples of sets where the sets are coming from this collection ai1 ai2 ait1 ait, right, because these are the only sets in which x belongs to, and then x, if it does x does not belong to all the three sets we are taking the intersection, then x will not be there in the intersection, right. So therefore, how many 3 sets we can select from this thing, that is only we should take. There are choose 3 possible ways to select 3 subsets in it, and each of them will contribute 1 for x because x belongs to each of them. So this will be choose 3 in the third term. In the fourth term it will be a plus, this is a plus term, the next term it will be a, sorry, this is a minus term, yeah, yes, this is a minus term, next term will be a plus term, that should be choose 4 by the same argument, and so on all the way to choose t. When we consider the sums over every t possible subsets of the k sets, only one collection of t subsets will contribute to it, because if the entire ai1 ai2 ait comes, then only their intersection will contain x, because if any other t subsets intersection of any other t subsets from a1 to ak is considered, then there will be one subset in it which does not contain x, because we know that only this t subsets contain x and no other, right. So therefore they will not contribute, only this can contribute. From now on, the next term onwards, there won't be any contribution from x, because we are selecting t plus 1 or more subsets, and there, because all the t plus 1 subsets there in any term cannot contain x, because x is only contained in these t subsets. Right, when you consider t plus 1 subsets and take the intersection, x won't be there in one of them, and in the intersection it won't come, so it won't contribute. So up to here only. The total contribution due to x is this: t choose 0 minus t choose 1 plus t choose 2 minus t choose 3 plus t choose 4, and all the way up to t choose t, and the sign depending on whether t was an odd number or even number, so minus 1 raised to t, right. And we know that this sum is going to be 0. Why? Because we have studied it earlier, that this identity we had studied, right, this identity we had studied. So yeah, we mentioned that this will easily follow from the binomial theorem, 1 plus x raised to t, expand it and put x equal to minus 1. Anyway, we do not have to redo it, right. So therefore, the contribution of an element x of the universe which belongs to exactly t sets in a1 to ak will be this, and this turns out to be 0. And a member of the universe, x of the universe, member x of the universe which belongs to none of this a1 to ak will contribute exactly 1, namely this first term, nothing else, right. Therefore, the total sum will have contributions only from the members of u which does not belong to any of a1 to ak, namely the members of x in ai complement intersection, right. And therefore, we are counting the cardinality of this thing by the procedure. So this completes the proof of that. So okay, this is the proof. Now what you can do is, we just remember remember the formula, and yeah, of course, so we can apply it even that way, but it's good to know the proof, of course. Otherwise, if you forget it, then we can reproduce it very easily. It's not a difficult proof, just have to understand how we count it. The counting was based on, rather than counting directly that okay, how many are there in u and then minusing how many are then each of ai and summing and then minusing. So, rather than that, we asked took an element of the universe and asked how much is this one contributing, and we saw that what should contribute is contributing exactly 1, what should not contribute is not contributing at all because of that identity, right. So, that was the proof. Now, we will consider some applications of this. Yeah, here is a simple problem. Find the number of integers between 1 and 1000 inclusive. Inclusive means including 1 and 1000 that are not divisible by 5, 6 and 8. So, we want to find the number of integers in between 1 and 1000, right. So, we are considering numbers in the range 1 and 1000 which are not divisible by 5, 6 and 8. Usually the sets we can say properties. The first property we are interested in is that how will you find it out, right. We can say that the property P1 corresponds to the property of a number P1 of n. That means n is, say, n is divisible by 5. What kind of numbers are divisible by 5? For instance, 0 we are not interested. After 1, 5 is divisible, then the next 10 is divisible, the next 15 is divisible, like that, right. Every 5 numbers you have one number which is divisible by 5. How many numbers are there from 1 to 1000 which has this property? For instance, 1 to 10 if you consider, there are 2 of them. So, easy way to do is divide 10 by 5, we get 2. Up to 13 if you consider, you can divide by 5 and take the floor. So, that is 2. Up to 26 if you consider, you can divide by 5 and take the floor, you get 5. For instance, up to 26 if you go 5, 10, 15, 20, 25, 5 numbers. It is not very surprising. What you do, what you just observe is every consecutive 5 numbers if you take, there is one divisible by 5 and next consecutive 5, like that. So, it makes sense to divide by 5 and take the floor, you will get the number of numbers divisible by 5. So, the number of numbers which have property 1 P1 from 1 to 1000 is clearly 1000 divided by 5, namely 200, right. So, we can say that A1 is the set of numbers such that n has P1, property P1, and of course 1 less than equal to n less than equal to 1000, right. Similarly, A2 we can define as those numbers n having property P2 and between 1000, because we are interested in 5, 6 and 8. This P2 is the property that n is divisible by 6. How many of them are there? 1000. This cardinality of A2 is easily calculated as 1000 by 6 floor. 1000 by 6 floor we can calculate to be 166, right. Yeah, 4 and 36, 166. And then A3 is the property that, A3 we can define as the property that P3 of n, and sorry, A3 is a set of numbers between 1 and 1000 which have property 3, namely P3 is defined as the property that n is divisible by 8. That also we can find by dividing by 8 and finding the floor. This is 20 has 125, right. 125. So, we can easily calculate the 3 sets. So, but why are we calculating these 3 sets? Because we are calculating these 3 sets because we are asked to find those n between 1 and 1000 which do not have properties P1, P2 and P3. It is easy to see that we are, if we consider U as this set, right, that means 1 to 1000, the universe is 1 to 1000. We are interested in A1 complement intersection A2 complement intersection A3 complement. That means the numbers, this correspond to the numbers which are not divisible by 5, this correspond to the numbers which are not divisible by 6, which are, these correspond to the numbers which are not divisible by 8, and we are interested in those numbers which are not divisible by 5 and not divisible by 6 and not divisible by 8. So, we are interested in this thing. So, which is essentially U minus A1 union A2 union A3, right. So, we know the formula for this thing. This is by the formula, it is cardinality of U minus sigma AI. Here I is only 1, 2, 3 and plus Ij, all pairs if you want to consider. You have to consider AI intersection Aj, this thing, and finally this will be one set A1 intersection A2 intersection A3 cardinality. This is what 1000 minus, this is what 3 sets, right. 3 sets are you know, we have already calculated this cardinalities of these 3 sets, namely first was 200, second was 166 and then 125. So, this is 200 plus 166 and 125. This is what we are. Then we are interested in, we have to add this for every pair. Every pair AI intersection Aj we have to add. Here we have A1, we have to do A1 intersection A2 for instance. What is that? That means it is divisible by 5 and it is divisible by 6. So, how is it divisible by 5 and 6? It is divisible by 5 and 6 if, yeah, it is divisible by 30, right. Sorry, see, if a number is divisible by 5 and sorry, 5 divides, suppose 5 divides n and 6 divides n, it is clear that 30 divides n, and any number which is divisible by both 5 and 6 is divisible by 30, right. So, it is essentially equivalent to counting the numbers which are divisible by 30 between 1 and n, and that is easy to see. This is this one, right. So, this is 33, you have to take floor. So, similarly we can find the numbers which are divisible by 5 and 8. Those essentially, it is very easy to see that if a number is divisible by both 5 and 8, then 40 has to divide it, and the other way, if 40 divides that number, then both 5 and 8 divides it. So, we can find the number of numbers divisible by both 5 and 8 by dividing by 40 and taking the floor, right, that is 25, right. Now, if a number has to be divided by both So, what we have calculated now is A1 intersection A2 is equal to 33 and A1 intersection A3 is equal to 25, and then now finally we are interested in A2 intersection A3 also. How much is that? This is the numbers which are divisible by both 6 and 8. So, the both 6 and 8 means here we have 2, 3, here we have 2 cube. So, its little thought will reveal that what we are interested in is this number 24, right. So, for instance, if a number is divisible by 6 and 8, it is definitely divisible by 24. Why? Because it is divisible by 3, 6, there is a 3 in it, because it is divisible by 8, there is 8 in it. So, 8 into 3, 24. On the other hand, if a number is divisible by 24, then of course 6 also divides it, because 24 is divisible by 6, 8 also divides it. So, you can count by asking how many numbers are divisible by 24. So, this is this, right. So, how many numbers are divisible by 24? 250, 6, so 25 by 3, right. So, that is 4, 41. Right. So, 125 divided by 3 is 41. So, we get 41 here, right. So, we get all these numbers which are see the cardinalities of the intersection of any pair. Now, we substitute in it 33, 25 and 41 in the formula. Yeah, 33, 25 and 41 in the formula, and the final term you have to minus this term. That means the numbers which are divisible by all the 3 of them, right. It should be divisible by 5, it should be divisible by 6, it should be divisible by 8. Of course, so that is equivalent to the numbers which are divisible by 5 into 3 into 8, that is 120, right. Why is it so? Because if a number is divisible by 5, 6 and 8, then definitely it is divisible by 120, because it is divisible by 5, there is 3 in it, there is also 8 in it, right. So, 8 into 3 into 5, so 120. On the other hand, if a number is divisible by 120, it is definitely divisible by 5, 6 as well as 8, right. So, therefore, we can just find out the numbers by dividing by 120, and then we get it. This is how much? So, 8. So, we can minus it off there. The final term we can minus it off 8. So, adding up these things we will get the answer, right. So, this kind of questions we can inclusion exclusion, typically we can apply this inclusion exclusion principle. I will just summarize it once again. So, we were interested in the numbers in 1 to 1000 which are not divisible by 5, not divisible by 6 and not divisible by 8. So, how we model the problem, that was the most important thing. We model the problem such that we can use inclusion exclusion, right, idea principle. So, first we noted that so this u can be considered this as this 1000, and it's there are 1000 members in the universe. Now, in this universe there are, it is easy to find how many members are divisible by 5, how many members are divisible by 6, or how many members are divisible by 8, or any of the combinations. That means how many members are divisible by 6 and 8. This kind of questions are easier to answer, because it is just a division by a certain number and taking the floor. So, now if we can easily find the cardinalities of the intersections, then we know we can apply the inclusion exclusion principle, because inclusion exclusion principle says if you want to find the members which does not satisfy any of the properties, then you can use it. I mean, first cardinality of the universe minus of the cardinality of the members satisfying individual properties, first property, second property, third, then two properties together with alternate sign, and three properties together, and so on, right. So, that is what we did here. So, now we will see another example. Here is a question about permutations. How many permutations of the letters math is fun are there such that none of the words math, is and fun occur as consecutive letters. Math, is and fun occur as consecutive letters. So, if you ask this is the question, math is fun. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters here, and these are all distinct letters, right, is not it? Right, nothing is repeated here. M is not there, A is only once, T is only once, H is only once, I is only once, S is only once, F is only once, U is only once, and N is only once. If we were just asking how many sentences can be formed using this thing, I mean without really how many permutations of these letters can be formed, it would have been easy. 9 factorial is the answer. But the question here is a little twisted. It is saying that okay, you can, I am asking for the permutations of these letters such that the word math does not come together there. I mean, for instance, you can make you cannot make a permutation EF UN math. This is a permutation of math is fun, but we are not allowed to use this thing. Why? Because this word math is coming together here, or nor I cannot form a permutation of, this is also a permutation of math is fun, but this is not allowed because is coming as a word here. So, you can I am only interested in those permutations where is will not come together. I mean, like you cannot read is or math or fun in consecutive positions, right. How many ways you can do this is what you are asking. So, now again we want to model this as as a problem where we can apply the inclusion exclusion principle. Let us say these 9 factorial permutations from our universe, 9 factorial permutations of the 9 letters, right, 9 letters in math is fun form the universe. These are the universe. Now, you see the properties we are interested in. I mean, what we want is those permutations which do not have those properties. First property P1 would be that the word math, this 4-letter word math appears consecutive in the permutation. Unfortunately, sorry, we can easily find this thing. This is easy to find. How many are there? Let us say A1 is the set of permutations. This is a subset of the universe such that math appears consecutive. Because what do? We have seen this kind of problems before. What we do is we think of this as one letter, say M dash, right, and then the remaining letters, how many are there? Out of 9 letters, we compress 4 into 1. So, that means we have 6 letters, right. So, we have 6 factorial ways of doing this. because what we do is wherever we insert, so wherever we see m dash, we insert this entire math. That is what I will do, right. What we do is, so m dash is fun, so total 6 letters, we take any permutation of this thing, we will insert that. See, we can insert m dash can be substituted by math, and the other way, suppose if you get a permutation where math is coming consecutive, I can substitute by m dash there, we will get a corresponding permutation here. So there are 6 factorial permutations which where math appears consecutive, right. Similarly, the second property we do not like is that ease appears consecutive in the permutation. Let us say the permutations, that means a subset of that 9 factorial permutations which have this undesirable property P2 is A2. The cardinality of A2 is also easily found because there are 2 letters which should not come consecutive, should come consecutive, appears consecutive, because if it satisfies property it appears consecutive. We can just press it into 1. So let us say this is I dash, right. Then it is out of 9 letters, 2 of the letters is compressed into 1, tied them together as if, right. Then we see that only 8 letters are there, right. So there are 8 factorial possibilities to do that. Similarly, property 3 is that fun appears consecutive, and the corresponding set A3, that means those permutations which has the word fun consecutive. How many are there? Because the fun can be now compressed into 1, say f dash, right. Now out of 9, 3 has become 1, so now 7 letters, so 7 factorial, right. So now you see that our A1, A2, A3 correspond to the permutations which have the property which do not desire. So A1 has the property that math comes consecutive positions, in consecutive positions. A2 has is a set of permutations where ease appears in consecutive positions, and A3 is the set of permutations where fun appears in consecutive positions. Now we know that the question asks for those permutations which does not have any of these properties. Neither math should come in consecutive positions, ease should come in consecutive positions, nor fun should come in consecutive positions. So if that is what we want, what we are asking for is this A1 complement intersection, A2 complement intersection, A3 complement. This is what we are looking for, which is essentially U minus A1 union A2 union A3. This is what we are looking for. If that is what we are looking for, then we can apply the inclusion exclusion principle by this formula, by using this formula. For every pair ij, we have to find the cardinalities of ai intersection aj, and then minus 3 cardinality. Now we have already seen that these cardinalities we know, this we already know, this is what 9 factorial, and here we know that this is 6 factorial plus 8 factorial plus 7 factorial, right. We have calculated it here, right. So 8 factorial, 7 factorial and 6 factorial, right. Now the next question is, how will you find this kind of cardinalities? So what is this? This says, say what about A1 intersection A2 cardinality of A1 intersection A2? A1 says math appears consecutively, A2 says ease appears consecutively. What we do is we substitute math with say m dash, one letter, we just tie them together as one word, one, I mean we will represent it as just one symbol, and is with one symbol I dash say. Now we have, instead of 9 letters, we have right, 3 plus 2, 5 letters, right. Here we minus 6 from this thing plus 2, because here we substituted m dash and I dash, total 5 letters we have. So this 5 letters can be permuted in 5 factorial ways. Now if it is 5 factorial, then okay, whenever we see m dash we just resubstitute math there, and whenever you see I dash we will resubstitute is there, right. So we will get those permutations where both math and is appears in consecutive positions. That is what this is, A1 intersection A2, right. Similarly, to find A1 intersection A3 is easy, because math has to be in consecutive position and fun has to be in consecutive position, right. Now 4 plus 3, 7, so 9 minus 7 plus 2, how much is that? That is 4 factorial ways we can do this thing, because what we do is we just replace this 4 letters with m dash, and then this one with say f dash. Now m dash, f dash and is, we have 4 factorial ways of permuting them. Now wherever we see m dash we can replace it with math, and wherever we see f dash we can replace it with fun, right. So that is not that here it what was, I mean this thing we should note that math and fun, they have different letters in it, math. So for instance, if you had math and hun, we will have more complication, because you know it can come in 2 different ways, either so no, of course there also we have to be careful, then this argument will not work. Okay, then also we will say that math hun, so after math hun has to come, therefore math hun has to be a continuous word, like that, right. But you can explore the other possibilities. For instead of math is fun, some other 4 letter words or some few words you can select, and suppose if you want to avoid them, what would you have done. Okay, similarly, okay, this argument, this method is same when I want to consider see A1, we have considered A1 intersection A2, A1 intersection A3, and finally A2 intersection A3. This also we can see, because is should come consecutively and fun should come consecutively, the same technique. So what we do is we substitute it with say I dash and this with f dash. So that is 9 minus 5 plus 2, total 6 factorial ways we can do, right. And finally, so that we can substitute in the formula here, right. So each of them, and we sum it up. And here the final term is the cardinality of A1 intersection A2 intersection A3. Then how will I do this? To find the cardinality of A2 intersection A3 intersection A6, right. A1 intersection A2 intersection A3. That means math should come consecutively, so this we can take as m dash, is should come consecutively, so the I dash, and then fun should come consecutively. So there are only 3 letters now, right, because every letter is blocked together. So 3 factorial ways of permuting this. So we can substitute back math is fun wherever we see that, right. So all of them will be consecutive in these things, right. Now we can put it there. Formula gives us the cardinality of U minus A1 union A2 union A3, and therefore right, that will give us the final answer, namely the number of permutations which has the property that math does not come in consecutive positions, is does not come in consecutive positions, and fun does not come in consecutive positions, right. This is what it will give. And routine technique, it was a Now I consider okay, two examples we considered. So, here what we can do is we can simplify the formula. This formula seems to be very tedious to write. So, we can simplify the formula in some cases. So, it is not very surprising that we can simplify the formula in some cases. For instance, we can go back to the formula. Sorry. Oh, okay. I just forgot to mention one more thing here. So, suppose you wanted A1 union A2 union AK only. For instance, yeah, up to now we were saying that I am interested in A1 bar intersection A2 bar intersection AK bar, which is essentially the cardinality of U minus union of U minus say A1 union A2 union AK, right. Now, of course, suppose if I am interested in the cardinality here, this one. So, it is not at all difficult, because this is U minus something plus something minus something like that. So, and this U, see U minus this is what I want, right. This what is this? Then if I want this, what I can do is I can take the remaining, right, because U minus this is actually this. So, this is the complement of this, right. So, as we know, A1 bar intersection AK bar by De Morgan's rule is essentially A1 union AK complement. So, if you want to find A1 union AK cardinality, so we are just finding U minus this cardinality intersection of AI complement, which will be by substituting for this from the formula, this will be U minus sigma AIs plus sigma ij AIJs. So, AI intersection and so on, right. So, this U and U cancel, but each of the remaining terms change the sign. So, we can write the formula like this: A1 union A2 union AK cardinality is sigma AI. So, this is I equal to 1 to k minus sigma ij. The signs have changed now, that is what, and like that finally we get minus 1 raised to k plus 1, because as of all the terms are taken, it becomes k plus 1. So, A1 intersection AK, because this k plus 1 only means that we have changed the sign to the next, because earlier it was minus, then it will become plus 1, earlier it was 1, then it will become plus 1. It is everywhere the sign has changed. Earlier it was a negative sign here, that has become plus, this was a positive sign here, it has become minus, and so on, right. All, for instance, whenever we were considering odd number of things together, that was given a negative sign in the earlier formula, and whenever we were considering even number of sets and taking the intersection, we were giving positive sign. Now, we changed, for even we give minus, and odd we give positive, right. It is not nothing big, it is just that we noticed that whatever earlier we were calculating was the complement of what we want here, this one, and just minusing off from U. So, therefore, all the signs changed and U disappeared. So, and okay, again coming back to the discussion where we just stopped, suppose we know that A1 cardinality is equal to A2 cardinality is equal to AK cardinality. that means all sets are of equal cardinality. Let us say this is alpha 1, just give a, so it is an alpha 1 uniform family we are talking about, all cardinalities are same AK, A1 to AK. Now A1 intersection A2, this is equal to say A2 intersection, A1 intersection A2, A3 and so on, all AI intersection AJ, if you any pair if you take and take the intersection, and this happens to be same alpha 2, means some problems because of the structure it may so happen that whichever pair of sets you take, their intersection is going to have the same cardinality. It may not depend on which two sets, it will only depend on the fact that there are two sets whose intersection you are considering. Similarly, say for any AI, AJ, AK if I take, and suppose the cardinality is alpha 3, it is not that always it like that, but suppose it is like that, and in general suppose when I consider I sets AI1 or T sets intersection AI2 intersection AIT, this is alpha T, then we can substitute the earlier formula by this formula. So, yeah, we can substitute the earlier formula by this formula alpha 0 being the cardinality of U minus k choose 1 alpha 1 plus k choose 2 alpha 2 plus k choose 3 alpha 3, and so not plus, these are minus and plus alternating, and for the typical ith term will be minus 1 raised to I k choose I alpha I plus final term will be minus 1 raised to k alpha k. Why is it so? Because you know, as we have seen when we are the first term alpha 1, it is the size of the singleton sets, and all singleton sets have the same size, namely alpha 1. So, there are k choose 1 of them, here we are adding them. So, therefore, we just add them together, we just k choose 1 times alpha 1. Similarly, the second term, any pair of sets if you take, irrespective of which sets, if you take two sets and take the intersection, it is always the cardinality is alpha 2. Then we just have to bother how many pairs we can take, that is k choose 2. So, therefore, k choose 2 into alpha 2 is the total sum there we would have got, right, plus. And next is a negative sign, the minus term, and any triple if you take, any 3 sets if you take from the k given sets. So, their intersection is always going to have alpha 3 elements in it. So, therefore, when you sum it up, what you can get is k choose 3, because there are k choose 3 possible ways of selecting 3 sets. So, k choose 3 is into alpha 3. So, this goes on, right, this formula. So, okay, this is definitely trivial, but just that we will have cases where this can be easily applied. So, we do not have to always remember the other formula. In many cases it may so happen that this property that when you talk about the cardinality of the intersection of T sets, that only depend on T, it does not depend on which T sets, just that how many sets intersection of how many sets you are taking only matter. So, we can apply this formula more conveniently. This formula means we can the simplified version, right. So, we can remember it easier. So, we will continue in the next class.